Most voice-to-AI apps rely on standard HTTP architecture. A client records audio, sends a request, and forces the user to wait for a response. This sequential approach creates an inherent, unavoidable lag. Building an agent this way forces the system to execute entirely dependent operations in a strict sequence. This diagram maps that standard linear pipeline. Audio must first process through a cloud speech-to-text service, push to a cloud LLM, and finally route through a cloud text-to-speech engine. Each network hop commands its own distinct processing time, stacking milliseconds until the total delay crosses into multiple seconds. When a user naturally attempts to interrupt the agent mid-sentence, the structural flaws are exposed. The active TTS playback collides with the new incoming audio, forcing the pipeline to drop the context state and start over. The Gestalt View repository provides a production-ready solution to this problem. It is an architectural blueprint engineered specifically to support stateful, interruptible voice interactions. The repository is constructed on 3 distinct pillars: a React and Vite edge client, an asynchronous Python audio worker, and a multi-tier LLM routing abstraction. This stack operates under strict engineering constraints. The system must hit sub-second baseline response times and tolerate abrupt human interruptions without losing the underlying conversational state. Achieving this requires abandoning the practice of wrapping a single provider's API. Instead, GestaltView implements a distributed structure that actively manages its own communication protocols. By decoupling the input and output protocols from the core intelligence engine, the system eliminates the bottlenecks of sequential processing. Engineering a true real-time agent requires isolating the listening phase from the generation phase. The client side runs on React 19 and Vite, operating specifically to capture continuous, raw microphone input without waiting for a user to trigger a submission. To bypass the handshake delays of standard REST endpoints, the client routes this continuous audio via WebRTC directly to a dedicated LiveKit server. This bidirectional pipeline maintains an open WebRTC connection directly to the LiveKit server on port 7880, eliminating HTTP overhead. A Python worker attaches as an active participant, pulling the incoming stream. Inside, 2 loops spin concurrently: Whisper STT for transcription and Cozy Voice for generation. The system relies on a precise voice activity detection threshold. The exact millisecond this threshold detects new human speech, the worker initiates its interruption sequence. Programmatically, this means explicitly executing a cancellation command on the active Python response task. The generation process terminates immediately. The worker severs the Cozy Voice TTS audio stream, halting physical playback. The AI physically stops talking, ensuring it never talks over the user. Halting the audio introduces a state management problem. The system has to retain the interrupted thought in its memory without pushing the remaining words to the speaker. The worker preserves the active API session context. Even though audio generation stops, the contextual data passes back up to the router for the next processing cycle. The user experiences this as active listening. The agent pauses because the asynchronous logic specifically interrupts the output loop to prioritize the incoming audio. Transcribing the raw audio is only the first step. Before that text reaches the LLM, the system requires immediate semantic grounding against an established data layer. The context weaver algorithm intercepts a raw text query, parsing and sorting the transcript into a strict 6-box matrix of who, what, where, when, why, and how. This parsed intent triggers a vector search against the database schema to identify matching data blocks. This retrieval process enforces a constraint that mandates exact lexical preservation. Standard RAG techniques often summarize their retrieved data. Applying summarization at this stage would overwrite the specific vocabulary, tone, and empathy required to scale the agent's persona. Instead, the system constructs a dense runtime context block. It extracts the exact user phrases from the database and prepends them verbatim to the final payload. If the vector search returns null, a rigid system prompt forces the LLM to reply, "I don't have specific information on that." The guardrail is absolute. By embedding behavioral constraints into the rigid database retrieval layer, rather than relying on volatile system prompts, the persona scales predictably without hallucinating off script. In production, any single third-party API will eventually fail. Relying on one provider guarantees eventual rate limits, timeouts, and complete outages. To prevent downtime, GestaltView routes requests through the AI flow abstraction, governed by a core route LLM function. This router segments incoming traffic, separating fast direct chat requests from heavier API-mediated actions. This waterfall chart maps the multi-tier fallback system. The payload first attempts Gemini Flash 2.0. On a timeout, the error handling hook executes an immediate cascade, dropping the payload to OpenAI GPT-4o, and then down to Llama 3 via Grok for extreme fallback. During this cascade, the system dynamically reformats the prompt envelope on the fly, translating the payload to perfectly match the specific API schema of the active fallback provider. At the absolute bottom of the routing table sits an offline fallback node. If all external APIs fail, this node intercepts the request and returns a structured null response. This hard-coded fallback architecture absorbs external API fragility. The system intercepts the failures internally, keeping the application online despite total provider collapse. When you examine the complete Gestalt View architecture, the edge voice loop, the semantic database, and the multimodal router operate as a single organism. A single user interruption flashes across all three pillars simultaneously. The WebRTC connection detects the input, the semantic layer verifies the context, and the router manages the fallback logic. Building an integrated system like this requires significantly more engineering overhead and complexity than deploying a standard API wrapper. But the most critical feature of this architecture is entirely invisible to the user. It is the exact absence of lag, amnesia, and downtime. Pushing beyond turn-based text interactions requires abandoning stateless HTTP models. Stateful, continuous WebRTC connections are the baseline requirement for running multimodal applications in real time. Reliable sub-second conversational performance is not achieved by waiting for better underlying models. It is built by engineering flawless, highly available infrastructure that routes perfectly around them.